Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
In this question, we have a wedge that is resting on top of a scale. Then now we have a hamster that is on top of the wedge. Now we gotta assume the hamster to be like a box, right, resting on top of the wedge. And we want to find what is the value that we read off on this scale when the hamster itself is able to stick onto the wedge, so it's not moving. So we're gonna analyze them as different objects, right, one by one. So first of all, for the hamster, we're gonna draw the free body diagram. The forces that it experiences will be first gravity, which is mg. Then there is the normal force from the wedge, and finally there is some frictional force, right, that allows it to stay onto the wedge. So these are the three different forces. Looking at the wedge itself, the wedge will experience a normal force that is coming from the hamster. It has its own gravitational force, mg, and it also exerts the frictional force, right? This action-reaction pair, so it has a frictional force that is exerted by our hamster, right? And we're going to assume that there is also an additional frictional force coming from the scale to prevent it from moving. In order to find what is the value that the scale reads, we can simply analyze the vertical forces. So only forces that are vertical, or the vertical components of all the forces, will add up to give us the overall downward force that the wedge will act on our scale, and this is what the scale will read out as. And so the different vertical components would come from Fs, right, the frictional force. It has some vertical components over here, right? Mg, everything is vertical, so its entire component, as well as the normal force, right? The normal force from the hamster. So we have to find what is this vertical component of the frictional force, as well as the vertical component of the normal force. We add them up together with mg, the big M, and we should get the value of the scale. So to find out what is Fs, right, the Fs is based on the mg, right? Since we know that the hamster is not moving, so the horizontal component of mg over here must be equal to Fs, right? To ensure that the net force in this direction is 0. So the angle over here we are given is 40 degrees. And so the angle, that will be the angle over here, right? This will be 40 degrees, which I've shaded. And so Fs would be equal to mg sine theta. Over here is 40 degrees as well. So the vertical component of Fs, let's call it Fs, vertical component Fsy in the y direction right? That would be equals to the original Fs, which is the hypotenuse, times sine theta. So this gives us mg sine squared theta. Next, we move on to the normal force. Alright, the normal force over here will be equal to the vertical component of our mg in this particular axis, right? Because we want net force to be 0. So the normal force will be equals to mg cosine theta. And bringing it down to this second diagram over here, we want the vertical component only. And so this will be, since the angle in this case will be over here. This will be 40 degrees, our theta. Alright, and so the vertical component would be sine. Oh, sorry. The angle is not there. The angle of our interest will be over here. This will be our theta. Let me draw it bigger for you. Right, this will be 40 degrees. And so the value of our vertical components, in this case on the right side, be equals to mg will be n times cosine theta should be mg cosine square theta. Finally, to get the total y component fy, this will be n of y plus fsy plus mg, which gives us mg sine square theta plus cosine square theta plus mg. We know that this is 1, right? Trigonometry. So we get mg plus big M times g, which is equals to 9.8 newtons. And this is expected, right? The mass, entire mass would be the mass of our hamster plus the mass of our wedge times gravity. Moving on to the next part. Now the hamster is allowed to slide down. And the interesting thing to note that when the hamster is allowed to slide down, what happens is that our friction Fs disappears, right? There's no more Fs involved, so there's no more vertical component from Fs that will contribute to our total vertical forces, right, in the y direction. So what we get is will just be ny plus mg, right? The Fs is no longer present because there is no more friction. So what we should get is the net force in the y direction would be just mg cosine square theta plus big M times g. We know that del theta is 40 degrees. So substitute that in, we should get 8.99 newtons, which is lower than our original scale of 9.8 newtons, which makes sense, right? If our angle is at 90 degrees, then our hamster will no longer provide any force, right? It'll be in free fall, and so won't contribute anything to the scale. And on the other extreme end, where the theta angle is 0 degrees, then our hamster would still contribute its entire mass right onto the scale, and so it'll be 9.8. And now since we are halfway in between, the value will be in between 9.8 and 0, so there'll be less than 9.8.
Homework pressure? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
For the first part of this question, what you need to look at is to find the acceleration constraint for the system. And to do that, we are going to look at the lengths of the different masses, or the positions of the masses, and we're going to find a relationship between them using the fixed length of the rope, right? LA, LB, to relate all of these mass positions together. Then we can differentiate the position to get the velocity, and finally velocity we differentiate further to get acceleration. So now we're going to write down some equations that are going to relate the lengths LB and LA. So LB is equals to YB, which is the YB minus Y3, which is the left hand side of the rope plus the right hand side of the rope. So that will be plus YB minus YA. Right. Same thing we're gonna do for the other pulley, LA. Length of the rope, LA, is equals to YA minus Y2 plus YA minus Y1. What we're going to do now is to find the common factor, which in our case is YA. I'm going to substitute that into the equation. Alright, so from the second equation, we can factor out what is YA. 2YA is equals to LA plus Y2 plus Y1. Right? And so YA is equals to half LA plus Y2 plus Y1. Go and substitute that into equation 1. You get LB is equals to YB is Y3 plus YB minus half of LA plus Y2 plus Y1. Now the next thing we're going to do is we're going to put all the constants over to the left, right? Constants being those that are not changing, such as LB, since LB is already attached. The LB is the length of our rope, and YB is also a constant since YB cannot change. The pulley itself is attached to the wall, the ceiling. So YB, LB, and LA are three constants which we can pull to one side. So LB minus to YB, as well as the YA. And the remaining terms that we have is negative y3, negative half y2, negative half y1. We're gonna multiply everything by negative 2, so we get y3, 2 of y3 plus y2 plus y1 equals to constants, right? Over here is some constant, so we're gonna just call them a constant. And this is the position equations, right, for the various masses. But we're not interested in that. We are more interested in the acceleration. So what we gotta do is we gotta differentiate the entire equation. And remember that when we differentiate a constant, what we get is 0. So what we get is actually 2 times of v3 plus v2 plus v1 equals to 0. Right? So the velocity of the various masses are in this relationship. To get the acceleration, we differentiate again. And this is our acceleration constraint that we have. So this is the important equation that we'll need to use later. In the subsequent part of the question, we now want to find what is the tension in string of A. That is over here. So we know that the tension will be felt equally for both M2 and M1, right, since they are connected by the same string. But we want to find what is the expression. Okay, so to do that, we're going to need to look at the look at the free body diagram first. So the free body diagram for our M1 basically only experiences gravity, which is M1G, and also the tension. So the Newton's equation for this, which is the M1 times the net acceleration, will be equals to T minus M1G. Alright, we're going to assume the downward direction is negative and upward is positive. Right, so this is the tension in A, TA. Same thing, we're going to do the free body diagram for M2. Experiences the same tension TA, and the magnitude of gravitational force is M2G. So M2A, M2A2, acceleration of second mass would be equals to TA minus M2G. We're gonna do this for our M3 as well. But remember, our M3 is connected by two of the ropes. Right, so there's actually two tension forces over here, TA, TA. So for the pulley at A, right, the pulley A, it experiences actually two downward forces, that is 2 times of TA, and one upward force, that is TB. Right, and this TB will be the force in which the third mass will experience. So M3 experience TB, which is also equals to 2 times of TA, and the downward force from gravity. So the net acceleration for mass 3 be equals to 2 times of TA minus m3g. So in order to solve this equation, what we'll need is to use the acceleration constraint which we have found earlier. That is a3, 2 times a3 plus a2 plus a1 is equals to 0. We will substitute the values. So we substitute from here, we can find what is a1. Right, from here we can find what is a2. In this equation, we're going to substitute a3 into here in terms of a2 and a1. From the first equation, we get a1 is equals to TA over m1 minus g. For a2 is TA over m2 minus g. So this gives us negative half TA times 1 over m2 plus 1 over m1 minus plus g, right? Because it's minus 2g multiplied by negative half, so this gives us plus g. Substitute this expression of a3 into our third equation. Alright. See that we have m3 times g over here, which we can bring over to the right hand side. Or actually from the right hand side bring to the left hand side. Since we want to find what is TA, and we bring the expression for TA to the right hand side. Factorize out TA. And finally we can get TA to be equal to m3 Alright, and we can actually simplify this expression a bit by dividing everything by m3 and then multiplying. Okay, so divide m3 and multiplying by 2, right? 2 over 2. So this will help us to make the expression a bit simpler. This will be 4 over 3 This will be 1 over m1 and 1 over m2. So this is our final expression for our TA. Finally, in the last part, we are given the numerical values of m1, m2, and m3, and we want to find, right, what is the acceleration for each one of them. So we already have the expression for TA. We're going to make use of this, given that we know the different masses already. So we just have to substitute in m3 to be 4 kg. Right, m3 is 4. m2 is 1.5. m1 is 2.5. We should get a value of 18.97 newtons. And using the previous equations, previous Newton's equation, we should be able to get the acceleration for each one of them. Right, so previously we have already these equations for here or here. We substitute in the value for TA, 18.97. Alright, same for here. And similarly for A3, right? A3 we just have to divide M3 over. A3 will be equals to 2 times of TA divided by M3 minus G. Alright, and we should get A1 should be equals to negative 2.2 meter per second square. A2 will be equals to 2.9 meter per second square. A3 should be equals to negative 0.32 meter per second square. So remember that we considered negative to be downwards and positive to be upwards. So basically M3 will be moving downwards, M1 as well, but M2 will be the one that's moving upwards. Right? And the last part, we are talking about why is it not in equilibrium, right? So from first look, we see that actually M1 equals to M2, sorry, M3 is equals to M1 plus M2. Right, so it seems like M3 should hang in equilibrium. And for it to happen, this would mean that our TB, our tension in the rope B, must be equals to M3 times G. It's equals to M1 plus M2 times G. However, the masses M1 and M2 are moving, and because M1 and M2 are moving, TB does not equate to M2 plus M1 times G, simply because the masses are moving. And as a result, TB does not equate to this, and so it's unable to balance the weight of M3, and thus M3 starts to accelerate.
Homework pressure? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
We want the rocket to reach the height of the loop in the same time it takes for the car to reach the X position of the loop. The rocket's motion has vertical and horizontal component. Select up for positive Y. Select the direction toward the loop for X. Toward Origin is the launch point. For the vertical component of the rocket's motion, we have two forces acting on it, thrust and weight. Newton's second law along y direction, we have F net in y direction is equals to F minus mg, which is equals to ma in y direction. Hence, ay, acceleration in y direction, is 8.0 Newton minus 0.5 kg multiplied with 9.8 meter per second square divided by 0.5 kg, which is equals to 6.2 meter per second square. The thrust, therefore the net force and upward acceleration are constant. Kinematics apply. We find the time t1 to get to y1 is equals to 20 meter by using y1 is equals to y naught plus v naught in y direction, initial velocity, multiplied with t naught minus t1 plus half of acceleration in y direction, t1 minus t naught whole square. We get 20 meter is equals to 0 meter plus 0 meter plus half of 6.2 meter per second square multiplied with t1 minus 0 second whole. We get 20 meter is equals to 3.1 meter per second square t square. We get t1 is equals to 2.54 seconds. Now horizontal motion. Horizontal motion az is equals to 0, and the horizontal velocity of the rocket is equals to the speed of the car, which is 3.0 meter per second, speed of the car. The time t1 is also the time for the rocket, so horizontally we reach the roof. X1 is equals to x naught plus v naught multiplied with t1 minus t naught plus half of acceleration in x direction, t1 minus t naught square, which is equals to x1 is equals to 0 meter plus 3.0 meter per second multiplied with 2.54 seconds minus 0 seconds plus 0 meter, which is equals to 7.6.
Humbug Baser? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
We have two separate motions. Select up for plus y for the rocket and for plus x the target's direction. The origin for the rocket is at launch position, and for the target the position where it is at the instant the rocket launches. The rocket will reach height y1 is equals to 30 meter starting from y naught is equals to 0 with initial speed v naught is equals to 0. Will need time t1 to do so. During the time, the target will have displaced to x1, which is our ultimate goal. For the rocket, two vertical forces act on it, thrust and gravity. Newton's second law along y direction. Newton's second law along y direction is F net y is equals to F minus mg, which is equals to ma. From where a is equals to F minus mg divided by small m, which is equals to 15 Newton minus 0.8 kg multiplied with 9.8 meter per second square divided by 0.8 kg, we get 8.95 meter per second square. Positive. The result is positive, thus upward, because the acceleration is positive here. Using the kinetic equation, since thrust is constant, there is also the net force as an acceleration. We have y1 is equals to y naught plus v naught t1 minus t naught plus half of acceleration t1 minus t naught square. We get 30 meter is equals to 0 meter plus 0 meter plus half of 8.95 meter per second square t1 minus 0 second square. We get t1 is equals to under root of 2 into 30 meter divided by 8.95 meter per second square, which is equals to 2.589 seconds. Hence T1 is 2.589 seconds. For the target, acceleration is 0. Same T1. We need the displacement during this time, which is equals to x1 is equals to x naught plus v naught multiply x t1 minus t naught plus half of acceleration of t1 minus t naught square, which is equals to x1 is equals to 0 meter plus 15 meter per second multiplied with 2.589 seconds minus 0 second t1 t naught plus 0 seconds. We get 39 meter. Thus the launch should commence when the target is 39.
हम तक पैसे? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
All right, so there's a diagram here of where you are and where the asteroid hits. This is Y, this is X, and where the asteroid hits. So there's this, and this. Now we're given launch A, B, C, D, and E. So let's see what we can do with that. So X equals 20 meters. So the distance away, I'm going to call that X0, is 20, kilometers. That's 20,000 meters. Okay. Okay, A through E are all headed in your direction. So we're going to do something with all of them. B, C, D, let's scroll down here, E. Okay, we have information on them. we're given a speed in meters per second, and we're given an angle in degrees. 520, 630, 750, 870, and 1,000. And then the angles are 14, 16, 18, 20, 22. 14, 16, 18, 20, 22. Okay, so the question is, in A, at t equals 20 seconds, what are the x and y coordinates? So x of 20, my goodness, it's not writing that very well. And then I'm going to get y of 20. I thought I was doing okay drawing this, but apparently not. Y of 20. Okay, well, x equals x initial, which is 0, plus v initial t, no, v cosine theta times t, and that's it. Y is going to be y initial, which is 0, plus v sine theta t minus 1/2 g t squared. So I can put this into a calculator. I'm setting g equal to 9.8. I'm going to set t equal to 20. I'm going to let v equal 520, and theta is 14. Make sure that I'm in degree mode on my calculator. And then x equals v cosine theta, and then multiply that times t. Okay? And y equals v sine theta, multiply that times t, and subtract off 1/2 g t, squared. Okay, I'm also going to divide by 1,000 so that I can state everything in kilometers. Putting that into my calculator now. Okay, so in kilometers, it is 10 kilometers and 0.56. Now, just putting in the other numbers for v and t. For the second one, v is 630, and theta, is 16. So now I get 12 and 1.5. 750 and 18. So I'm just putting this into Desmos, and I can just change this stuff easily. It's going to give me 14 and 2.7. 870 and 20. 16 and 4.0. So these are all in kilometers again. And last one is 1,022. That would be 19 and 5.5. Okay, let's see what we got next. Plot these coordinates. Okay, so I need to plot these coordinates. So, okay, I have a plot up here, but I'm not thrilled about how I started it. I also have room up above. I didn't realize I had all that room up above. Okay, plot these coordinates. 10, 12, 14, 16, 19. Okay, well, that's good. So, can I take this and move it up? Am I that good that I could do that? Not terrible. Don't know where that came from. That was probably there. Don't know what that is. Okay. Let's get rid of that. Now, I think I'm concerned about 20. So I'm going to put 20 the whole way over here. Yeah. So 10, 12, 14, 16, and 19. Well, this is 15. So 12, 14, 10, 12, 14, 16, 19. This is kilometers. Okay, now, this goes up to 5.5. So I'm actually just going to bring it all the way up to 8, 4, 6. Okay, so this is at 1/2. 10, comma 1/2. So that would be like way down there. This is at 12, comma 1.5. 12, comma 1.5. 14, comma 2.7. 16, comma 4. 19, comma 5.5. Okay. All right. Sketch a curve through the points. Okay, well, let me make my points bigger. At least I'll try to. And now I need to sketch a curve through these points. Looks pretty linear the way that I've drawn it. Pam. Okay. So this is an idea of what you would see with the approaching rocks. Interesting. So it actually looks kind of like a plane, although I'm sure it would go out in all directions. So it would look almost like a disc falling from the sky. And that's why it's called Curtain of Death, because there would be rocks everywhere falling. Very interesting. Thank you for watching.
हम तक पे से no more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
The car as a particle is in uniform circular motion. The force causing circular motion is static friction between the road and the car tires. The centripetal acceleration is given by equation centripetal acceleration is equal to v square upon small r is equal to 25 meter per second square divided by 100 meter, which is equal to 6.25 meter per second square. The acceleration points to the center of the circle. Hence, by Newton's second law, the net force is equal to mass into acceleration 1500 kg multiplied with 6.25 meter per second square. We get 9380 Newton towards the center. The force is provided by static friction, hence F static friction is equal to Fr, which is 9380 Newton.
Humpuk Pesser? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
In this problem, we're going to talk about circular motion. So consider that we have a particle undergoing circular motion with a radius r, and we want to describe the forces that are acting on this particle. Let's say that this is the particle here. So we can decompose the force into two components. The first one is a centripetal component that points towards the center of the trajectory, and the acceleration associated with this force has a magnitude of v squared divided by r. V is the linear speed, and this is responsible for the change in direction of the trajectory. There's also the tangential acceleration that only appears when there is change in the speed itself. Okay. So in our problem, we have a car that has a mass of 1500 kilograms and is moving with a speed of 15 meters per second in a circular trajectory of radius 50 meters. And our goal is to find what is the friction force that acts on the car. Well, notice that the forces that act on the car, let's say that this here is the car, okay, the trajectory, the circular trajectory is in this plane like this. The forces that act on the car are the normal force upwards and the gravitational force downwards, and also the friction force. And since the car is moving in a circular trajectory and the only force on the plane is the friction force, then the friction force must be pointing inwards, okay? Because the car is not changing its speed, then there is only a centripetal acceleration. So the force, the friction force, must match the centripetal force. Okay, so the friction force is the centripetal force, and it's equal to the mass times v squared divided by r. So the mass is 1500 kilograms, v is 15 meters per second, and r is 50 meters. So the frictional force is 6,750 newtons, which is our answer.